Every crystal face is going to have a different structure, and because of that it's going to have a different surface energy. Let's look at the relationship between surface structure and surface energy. So we know that molecules at any surface, whether it's solid or liquid, have a higher energy than ones in the bulk because they're missing interactions. We're missing bonding, and whether that's non-covalent bonding between molecules like van der Waals interactions, or it's covalent bonds. In any case, it's going to raise the energy of those atoms on the surface. When we modeled the surface energies of liquids, we used to use a simple cubic model because we didn't have detailed information about the surface or the bulk. With solids, it's different, at least crystalline solids. We know exactly what the connectivity is in the bulk, and when we look at the surfaces, we can see what the bonding is there. So what we're going to do is examine what the coordination number is for each atom in the bulk versus a particular crystalline face, and we'll be able to see how many bonds were broken. In the case of a metal, it's going to be a metallic bond. In the case of a covalent network solid like a diamond, it will be a covalent bond. In the case of a salt crystal, it's going to be an ionic bond. And in the case of a regular soft covalent solid like a solidified hydrocarbon, the bonds that are broken are just van der Waals interactions. But in any case, we'll be able to see how many there were in the bulk and how many on a crystalline face, and take the difference to know how many bonding interactions were broken. And because even within a given crystal structure we can cleave it along many, many different crystal planes, we actually have to examine each crystalline face separately. They're all going to have different properties. Because the surface energies are going to vary and be different for different crystalline faces, that means that the ability of things to adsorb to those surfaces will be different. And since adsorption is the precursor to catalysis, the catalytic properties of the different crystalline faces are going to be different. So let's look at some crystalline faces. All the faces in this presentation were generated using the Surface Explorer website, which I urge you to spend quite a bit of time playing with this software, because it will allow you to take a different crystalline face and tilt it and look at it from different angles and really see what the connectivity is. Okay, so we're going to work with an Fcc structure here, and we're looking at the 100 face for this crystalline face. Well, for any Fcc, we're always going to have the coordination number in the bulk is going to be equal to 12. But to get the surface coordination number, we actually have to look at it. Okay, so you can do this drawing it out with a pen and paper. It's better to play with this software because you can actually see. So if we look at one of these atoms on the surface, we can see that it's easy to see. I'll draw it in red over here. Let's look at this one. We can see that it's bonding to that atom and that atom and that one and that one, and it's not touching to the atoms that are corner to it. So it's got 4 within the surface. If we look below any atom, we can see it's sitting on 4 other atoms, 1 here, and 1 that's hidden. So that means that the surface coordination is going to be 8, right? 4 plus 4. And if we turn this sideways, we can see that there's no touching between this layer and then the second layer down. And you actually do have to check for that, because in some crystal structures you'll see that an atom in the top layer is touching 2 layers down. But here it's not. So since we have 8 at the surface, we had 12 to begin with, we lost 4. Okay, so that's the Fcc 100. Let's stay in that same crystal structure, but look at a different face. The 110 face. Well, once again, we already know this is going to have to be 12 as the bulk coordination number since it's Fcc. But what about the surface? Well, if you look, the surface is kind of corrugated. There's these rows here. Well, let's look at one of these. Here, if we look at this carefully, we can see that these surface atoms are touching the atom behind them and in front of them, but they're not touching any of the atoms to the side of them. They're not touching the atoms in this row. We go down to the next sort of sublayer, we can see that each of these atoms is sitting on 4 other atoms. So we could draw like this one, for instance, is sitting on this one, this one, this one, and this one. So we've got 4 connections there. That's that. And then if you turn this sideways, you can start to see that each of these atoms is sitting directly above, or is just touching an atom, not in this layer, but even one down from there. And actually, you can sort of see that here. These are touching. Actually, that wasn't the best choice of color. You can see that these are touching. So every atom is touching 2 in its row, 4 below it, and then 1 even further below it there. Okay, so we have a surface coordination number of 7. We started off with 12, so we lost 5. So notice that this surface is worse, it's higher energy than the other surface. And it's something you can sort of tell by eye, that this 1,0,0 surface, the atoms are more exposed, they're less bonded than in the previous example we looked at. Okay, and we'll look at one more, the 1,1,1 face. And here we can see that, I'll draw this in red, we can see that each of these atoms is sort of in the center of a hexagon. So I can draw 6 little connections to atoms in that same surface layer. And if we look underneath, we can see that each of them is sort of cupped by 3 other atoms on the layer beneath. Well, that means that we have a surface coordination number of 9, which means that we only lost 3. So this is a much better plane. And you might remember that we said that the 1,1 plane is the close packed plane for FCC. And the close packed planes, because you're losing fewer bonds when you generate a close packed plane, those are the lowest energy. So if we wanted to annotate this, we could say this one was the best. And moving backwards, this one was the worst because we lost more bonding interactions. So to summarize that, we said this was close packed, we lost fewer bonds, we lost only 3. Here we lost 4, and in the 1,1,0 one we lost 5. So we expect that the amount of energy the amount of bonds that we've broken is going to be proportional to the surface energy. So we know that qualitatively we will have this trend for FCC. We'd have to go through this analysis separately for every different type of crystal structure. All right, well, we can actually use this in a quantitative sense to estimate values for the surface energy, just like we did with liquids. We don't use the energy for vaporization, we use the energy for sublimation because we're going from the solid all the way to the gas phase. So this represents the energy to take a mole of the solid and break it up entirely into gas. If we divide that by Avogadro's number, now it's the energy per atom, not per mole. And because we're not breaking all the interactions, just a fraction of them, we need this. So this is the fraction of lost interactions. We could annotate this if we wanted. When we use that simple cube model to do the surface tensions of liquids, we used a fraction of 1/6. We were saying that the liquid molecules were cubes and that the face that was on the surface lost its bonding. So we had a fraction of 1/6. But here we're going to actually specify a number, and that number is going to be different for each of these, right? So it could be 5/12 for this one, or sorry, 5/12 for this one, but only 3/12 for that one. A naught is going to be the area of the face per atom. So this one's going to be a little bit tricky to calculate. So I'll do an example for you in the next screencast.